So this question is how to find this generating function. That is the biggest hurdle. To do that, we have to find out the generating function by the so called Hamilton-Jacobi equations, right. So I call this as the HJ equations. So what are so HJ equations are the first order, just some information, are the first order non-linear partial differential equations whose solution gives the generating function phi, which in turn gives the symplectic map, okay, which converts from one Hamiltonian system to the other. So this question is, what is this equation? Okay. So this question is, once we have solved the Hamilton-Jacobi equation, we can readily find the solution to the Hamiltonian via the set of implicit equations. So what I said is the following. So once the HJ equations, once a general solution to the HJ equations is found, the general solution to the HJ equation is found, then the solution to the Hamiltonian system is found via the generating function, right, generating function, okay, in the form of an implicit equation, right. We are going to see what do I mean by this statement, okay, very soon through an example. Okay. So let me now describe this Hamilton-Jacobi equation. Let us see what is this equation. So note, and we are going to do that in the general case, okay. So suppose we are given a generating function. So suppose there exists a generating function phi, right. There exists a generating function phi such that the transformed Hamiltonian H hat is 0. So what am I saying is, the generating function is such that the Hamiltonian in the new coordinate frame capital P capital Q is identically equal to 0, right, as simple as that, right. So then it implies that the symplectic map produced by phi, leads to the following set of equations. Qk dot is partial H hat partial Pk, and Pk dot is partial H partial Qk, right. This is the regular set of Hamilton's equation. Also the symplectic map produced by phi leads to the following. Notice that since H hat in this new frame is 0, so the derivative will also be 0. From here I see that my Qk will be a set of constant and my Pk's are a set of another constants, right. So which means that since I have the Hamiltonian in this transformed plane, phase plane is 0, let us go back few slides to the equation I am referring to. Notice this particular equation. Notice this equation that I had described that I had written to describe phi. So now I am saying in this equation I am going to plug H hat equal to 0, and when we do that, we get that. So this relation was let me call this relation as D. So from the relation D, I get that h of t comma q comma p bar plus the partial phi partial t is equal to 0, because h hat is 0, and that so notice that my final relation should not contain any conjugate variables, because conjugate variables are a new set of variables which we have to describe later. So we substitute, we eliminate pk's using pk is equal to partial phi partial qk. Eliminate pk equal to partial phi partial qk. Okay, that is by our Hamilton's, well, that is the relation obtained from the generating function itself. Okay, so when we do that, I see the new set of equations are as follows. I see that h of t comma q bar comma, so we get a vector set of relations, namely partial phi partial q1, partial phi partial q2, and so on, partial phi partial qn, right, plus partial phi partial t is equal to 0, right. Okay, so this is the equation we were after, and this is my well known Hj equation or Hamilton-Jacobi equation. So to find the generating function, we have to solve this first order nonlinear partial differential equation. So this is dot dot dot, and let us see what is the power of this equation. Okay, so let us look at an example. We revisit our example of geometric optics. Where our functional j of q bar was integral n of q bar times 1 plus q bar dot square dt, right. Okay, so in this example, recall that my Hamiltonian h of t comma q bar comma p bar is equal to this following function, minus n square minus p square minus p1 square minus p2 square. That is what we had found in that example, and we are going to replace our pi's by the relation for the generating function, right. Pi's by del phi del qi, and so my Hamilton-Jacobi equation in this case will be h plus del phi del t is equal to 0, or my h is the following, but I replace my pi's by del phi del qi. So I get that this is minus n square, n itself is a function of q, minus p1 is partial phi partial q1 square minus partial phi partial q2 square. This is plus partial phi partial t, this is equal to 0. Okay, so we can simplify this equation a little bit by taking this partial phi partial t on the other side and then take the square on both sides. I see that this is partial phi partial q1 square plus partial phi partial q2 square plus, after all the simplification, plus partial phi partial t square, this is equal to n square. Now it seems, or I can write down this equation in a more compact form. This is my Hamilton's Jacobi equation. So this is grad of phi, the absolute value square is equal to n square, where my grad is defined to be partial q1, partial q2, partial t, right. Notice that this equation, if this equation is suppose this equation is independent of t, there is the phi is such that phi is independent of the independent variable, then this equation is nothing but the Poisson equation, right, the generalized Poisson equation. But given the time derivative, this is the well known Econal equation for geometric optics. So Econal equation. So people working in geometric optics will readily know this this equation. Okay. So I am not going to go beyond and go ahead and solve this because it is quite complicated, but we will look at a few more relations that should be true for phi, and we will look at some simpler case in order to see the power of Hamilton-Jacobi equation. Okay. So few more concepts I want to introduce. So I call my phi, which is phi of t comma q bar comma q bar. Well, I call this as phi of t comma q bar comma alpha bar, where alpha bar is a constant, right. Where did this substitution come from? Again, go back few slides. If we go back few slides, notice that the symplectic map for the Hamilton-Jacobi equation led to the following, that q is equal to alpha. So that is the reason that we substituted q bar to be alpha bar, where alpha and betas are constants. Okay. So these are all constants. So suppose, so this is complete, right, complete. So the definition of complete has to do with the definition of the necessary existence of derivatives. So we see that this generating function is complete if phi has continuous second partial derivatives, with respect to its variables, with respect to the variables q, k, alpha, k. Notice that I am conveniently, on some occasions I am conveniently saying that alpha k is constant, and on some other occasions I am conveniently saying that alpha k is variable. There is no confusion because alpha k is nothing but our coordinates q, capital Q. So when I say that, when I take the derivative with respect to a variable, they can be conveniently switched with capital Q, right. So what I am saying is alpha bar can be thought of capital Q bar whenever convenient, right, whenever convenient, right, can be thought of as capital Q bar whenever convenient. Okay. So this is complete with so if second partial derivative exists, and what I have is the following Hessian matrix, which is partial to phi of partial q j partial alpha k of j comma k. This is the Hessian matrix is non-singular, right. So let us say we have a situation where we can invert the relation for phi, or phi is complete. So in that situation I can write down the relation between the Hamiltonian system and the Hamilton-Jacobi equation. So what I am trying to do is writing down the connection between the Hamiltonian and the Hamiltonian system and the Hamilton-Jacobi equation, right. Where does Hamilton-Jacobi equation fit in, right, and I state this result in the form of a theorem. theorem 16 says, the theorem by Hamilton-Jacobi says that suppose I am given a function phi, which is phi of t q bar alpha bar is a complete, it's a complete solution to the Hamilton-Jacobi equation. So where is my solution to the H-J equation? Well, I need to number some equations here. So my H-J equation is this following. So this I term it as A. So this is my H-J equation. So equation 1. Okay. So suppose phi is a complete solution to equation 1, then the general solution to the Hamiltonian system, the general solution to the Hamiltonian system, right, the general system, this system q dot k, which is given by del h del p k slash p dot k, which is minus del h del q k. So the general solution to the Hamiltonian system is given by the following set of equations, is given by del phi del alpha k is equal to minus beta k. So these are an arbitrary constant. This is an arbitrary constant, and the second relation is del phi del qk is equal to pk, right? So well, this is my generalized momenta. So this is my momenta. Okay. So what this theorem says, I have stated this theorem without proof, is that once we have solved the Hamilton-Jacobi equation and find the generating function, then we can directly find the extremal solution q via the set of these two relations given by 1 and 2 from the generating function. Okay. So this is what we have done. So this question that we have to ask is how to obtain. So this is the gist of this theorem, how to obtain a solution based on the Hamilton-Jacobi equation, right? The answer is as follows. We determine Hamiltonian H. So we start by finding the Hamiltonian function H, right? Then the next step is we form the Hamilton-Jacobi equation or the H-J equation with the help of the Hamiltonian. The third step is we find the solution, the complete solution phi, right, of the Hamilton-Jacobi equation, not phi prime but phi, right, which is the generating of the H-J equation, right. Then the fourth step is we set up, the moment we know phi, we differentiate phi with respect to the constant and set up these two equations. We set up especially the first equation, beta k is negative phi del alpha k, where beta k's are constants, an arbitrary constant, and finally we solve for n equations. We solve for n equations in D. We solve for n equations in D. So these are my set of n equations to find my answer qk, which is my extremal solution for qk to get the general solution, the solution q bar of t comma alpha bar comma beta, right? Okay. Okay, let us see this strategy with the help of an example. So this is the example I have in mind. So find extremize f of y given by this functional from a to b y prime square dx. Now, this is a very simple example, and I do not want to solve this example using Euler-Lagrange, but I want to use the Hamilton-Jacobi equation, and we will show that the solution obtained is identical to the one obtained by Euler-Lagrange. Okay. So, the first step, the step A is to find the Hamiltonian. So, the Hamiltonian is given by, in our previous lecture we have shown, if this is my f, my Hamiltonian is given by minus f plus y prime p, right, where my p is partial f partial y prime. So, by plugging in the value of f, I see that this is also equal to y prime square, and this is also equal to p square by 4, right. Now, from here I see I can find the Hamilton-Jacobi equation. So, that is my step B. My Hamilton-Jacobi equation is, my independent variable this time is x. So, x is my independent variable, right, independent variable. So, the derivative partial phi partial t will be partial phi partial x. So, I have the equation as follows: del phi del x plus the Hamiltonian. The Hamiltonian, which is h of x comma y y prime, right. So, comma p, right. Now, I replace my p with del phi del y, right. Note that that is what we have said earlier. We replace, well, we replace p by del phi del qi. In our case, qi is y, or the dependent variable, okay, and set it equal to 0. So, when we do that, my Hamilton's equation becomes partial phi partial x plus p square by 4. So, Hamiltonian is p square by 4, but p square is phi del y. So, it becomes 1 by 4 times del phi del y whole square set equal to 0. Now, note, so from here on we have to solve this equation. So, the step C tells us to find the solution to this Hamilton-Jacobi equation. We assume a solution which is variable separable. So, assume phi of x comma y to be of the form ux plus vy, right. So, separable solution. Right now, we are assuming that I can separate my solution. In a later lecture, I will show how to separate this solution. So, assume a separable solution. So, which means that this equation tells us that du dx so du dx plus 1/4 dv dy square is equal to 0, and from here I see that these two are equal to each other. Note that this is completely a function of x, this is completely, so this is a function of x, this is a function of y, and they can only, so let me first rewrite in this form. So, this is equal to minus of 1/4 of dv dy square. Now, this is a function of x and this is a function of y, and that is only possible when both are constants, since they are equal to each other, right. So, which means my du dx is a constant. Let me call the du dx a constant to be minus alpha square, right. Okay. So, from here I see that u of x is minus alpha square x plus a constant gamma, right. Now, this means that 1/4 from the Hamilton-Jacobi equation, plugging in du dx, which is minus alpha square, I get that 1/4 dv dy whole square minus alpha square is equal to 0, and from here I can solve for v of y, which tells me that v of y is 2 alpha y plus beta. I do not care about the sign of alpha here because alpha is a constant, it does not matter, right. So, I have retained the positive sign here. So, which means my generating function phi of x comma y is ux plus vy, which is also equal to minus alpha square x plus gamma plus 2 alpha y plus beta, and I see that so once I have the extreme the generating function, the next stage is to set up partial phi partial alpha equal to a constant, let us say equal to a constant. Well, we have note that in phi we have 3 constants, alpha, gamma, beta. If we take the derivative of phi with respect to gamma or beta, we are going to get 1 is equal to a constant. So, there is no new relation. So, differentiation with respect to gamma and beta gives an identity, 1 is equal to a constant. So, there is no new information. So, this is quite trivial, right. So, now we are going to differentiate. So, we are going to differentiate with respect to the constant alpha, which is this constant, right. So, when we set up this equation, I see that the following relation comes out. With respect to alpha, when we differentiate, I see that 2y minus 2 alpha x is equal to a constant, right. Or I see that the equation is y is equal to alpha x plus a constant, which is nothing but the equation of a straight line, and that is the solution to, or that is the extremal that we have found directly from our Hamilton-Jacobi equation. Let us, before we wrap up our lecture session, let us quickly look at the same equation or the same formulation via the Euler-Lagrange condition. Let us find the extremal via Euler-Lagrange. So, notice that the functional f of y is integral from a to b y prime dx square, and note that the Euler-Lagrange equation gives me partial f partial y prime d dx is equal to, when we plug in, well, minus partial f partial y. When we plug in f, I see that I get y double prime is equal to 0, and the solution to this gives me y is equal to mx plus c, which is a straight line. So, the solution via the Hamilton-Jacobi matches with the solution via the Euler-Lagrange. So, hence Hamilton-Jacobi method is an alternative to the Euler-Lagrange method, and it is quite a powerful alternative. Now, in the next lecture, we are going to look at in more depth the power of Hamilton-Jacobi equation, and also look at the cases or the conditions under which we are able to separate variables in our generating function. So, thank you very much for listening. Thanks a lot.